All right, section 9.1 is called Determining Probabilities. As we start, most of the time, we always have to start with a little bit of vocabulary of what we mean by things. That's where we're going to start this time as well. The first thing we're going to talk about is what we mean by an experiment. So an experiment is an activity whose results can be observed and recorded. So that might look like scientific experiment. I mean, that definitely counts. We're going to be looking more at things that have a predictable kind of outcome. So when we are talking about experiments, we're not necessarily going to be looking at things in science. We're going to be looking at perhaps some games, expectations of rolling dice, or things like that. We're going to talk about dice a little bit today. We might be looking at expectations when somebody's pregnant. Do they have a boy or a girl? We'll do that at some point in this chapter. We're going to be looking a little bit of this chapter at gaming like roulette, card games actually as well, and the lottery. So lots of fun, not so good for us kind of things. And we'll talk about some of that too actually as we go through. Outcome. Outcome is just a possible result of the experiment. It can be a positive outcome, a negative outcome, an indifferent outcome. It's just anything that could possibly happen. And then the sample space is just the collection of all those things. So when you think about like rolling a die, okay, an outcome is rolling a number 1. All of the outcomes would be rolling a 1, 2, 3, 4, 5, or 6. It's just a collection of those objects. And then an event is any subset of the sample space. So it could be a single thing happening, like rolling a 1. That's an outcome. It's also an event. Or it could be more of a description that is more inclusive, like rolling an even. Right? That would include 3 possible outcomes, individual outcomes, but still all describe one event. Okay, so that's the language we're going to be using. The first theorem we have is Theorem 9.1, and it's called Bernoulli's theorem, or the law of large numbers. It simply says that if an experiment is repeated a large number of times, then the probability approaches a fixed number. This is the idea that if I took a coin and I flipped it 50,000 times, I would expect that I would have about 25,000 heads and about 25,000 tails. It would be about 50-50. Okay, that's what Bernoulli's law of large numbers says. Probability is actually calculated by taking the number of events. This notation is one that we use in Elementary Math 1, so some of you have seen it before. This is the number of outcomes, we'll say it that way, based on the language we're using, in event A. So maybe that's rolling an even. And dividing by the number of outcomes in the sample space. So again, if we were looking at something like rolling an even, we would say, oh, there's 3 possible ways I can roll an even, so 3 is going to go in the numerator. How many ways are there of rolling the die altogether? 6, so we put 6 in the denominator, and then we would reduce. So the probability of rolling an even is about 1/2, okay? And that would be this fixed number that we're referring to in Bernoulli's law of large numbers. So does that mean that if I roll the die, 10 times, I'm going to get 5 evens? Well, no, it doesn't, for several reasons. But the issue is that it's a probability that we approximate over time. We get it close to over time. All right, mutually exclusive events. There are 2 phrases that we're going to come across. Today's is mutually exclusive. I can't remember if it's in 9.2 or later. We're going to come across another one that sounds the same but means something different. The mutually exclusive events are simply events that have nothing in common, like rolling an even and rolling an odd. Nothing in common, right? It doesn't mean that they don't affect each other. They do affect one another. If I roll an even, I didn't roll an odd. I mean, obviously there's an effect on that. If I'm pregnant and I'm having a girl, then I'm not having a boy, right? I mean, there's an effect on that. But I can't have both things happening at the same time if the events are mutually exclusive. I can't roll both an even and an odd, okay? This notation here at the bottom is notation that some of you have seen before. It's not something that I'm terribly concerned about if you haven't, but all it's saying is that A is one set, B is the other. This notation, for those of you who have had Elementary Math 1, what is that notation? Intersection. Intersection means what they have in common. Okay? Does anybody remember what that fancy 0 with a line through it is? It's the empty set. The empty set means that it's a set with nothing in it. So this is simply saying A and B have nothing in common. It's just the math symbols to show that. Okay? We're going to use a few more math symbols in here too as we go. All right, Theorem 9.2, that's our next one, says the following. If A is any event and S is the sample space, then 0 is less than or equal to the probability of A is less than or equal to 1. Let's talk about our dice again. We're going to keep calling back to our die because this is an easy example that we all can visualize pretty quickly. What is the probability that I roll a 0 on a die? It's 0 because there's not a side on my die that has no dots, right? That is a 0 probability. Can I get something less than 0? Well, no, 0 means it cannot happen, right? All right, so what's the probability that I roll something 1, 2, 3, 4, 5, or 6? The probability. How likely is it going to happen? 1. It's a definitely thing. I mean, one of those numbers is going to come up. Okay, so those are the two sort of extremes. The probability that I roll nothing between 1 and 6 is 0. The probability that I roll something between 1 and 6, that's actually 1. If I roll something bigger than 6, again, probability of 0. But if you want something in between, you know, any of those individual events, the probability of rolling a 5, the probability of rolling a number less than 3, those kinds of things will all be numbers between 0 and 1. And they relate to the percentage section that we just did, right? So this is like this 0 to 1 is between 0 and 100%. It's a 0% chance. That means nothing. There's no way it's going to happen. 100% chance means that it definitely can. When you look at the weather, this is a very good example. They're never going to tell you that there's a 150% chance of rain, right? They're usually not going to tell you there's a 100% chance of rain because they want that little out in case they're wrong. But they're going to tell you something between 0 and 100. That's a probability. It's expressed in a percent form, but it is a probability, all right? Theorem 9.3 says that the probability of an event is equal to the sum of the probabilities of the disjoint outcomes making up the event. It's a really wordy way of saying something you probably already knew if I gave you an example. So we're going to do an example. Let's say, for instance, that we did the probability, we talked about this a minute ago, that we roll an even. Well, one way to do that, like we discussed just a moment ago, is to find the number of evens divided by the number in the sample space S. And we said that that was 3 out of 6, right? I'm going to leave it as 3 out of 6 for the moment because I'm going to show you another example of how to think about this. What this is telling you is one way to do this instead is to count up the number of ways of rolling a 2 divided by the number in the sample space, plus the number of ways of rolling a 4, divided by my number in the sample space, plus the number of ways of rolling a 6, divided by the number in the sample space. What is each one of those probabilities equal to? 1 over 6, right? 1/6 plus 1/6 plus 1/6. So that's the same 3 out of 6 that we got the first way that we thought about it. They're 6s. They do look a little bit funny. Oh, those are S's. Okay. Yeah. This says S for sample space. Yeah, those are S's. S and 5 are terrible notations in mathematics because they just look, it's like T's and pluses, right? Not good. Yeah, S for sample space is what we're using. All right, the kicker to doing this is there's one word up here that has to be satisfied, and it is for this particular example. The word is disjoint. What does disjoint mean? Separate. It also could be thought of as mutually exclusive, right? Right? Disjoint, they have nothing in common. All right, so rolling a 2, rolling a 4, rolling a 6, it can't happen at the same time. So those are disjoint events, but they make up the overall event of rolling an even. So that's all this theorem is saying. All right, let's look at another one. This is related, Theorem 9.4, to this mutually exclusive idea. It says if A and B are in fact mutually exclusive, then the probability of the union, okay, A union B, is the probability of A plus the probability of B. This is just what we did in that last example. A and B are mutually exclusive where they're disjoint. So this is basically saying the probability of rolling, like I said a minute ago, an even would be the probability of rolling each one of those events then separated out. And union just means the two things, either one of them happening. That's all union means, either one of them happening. It's like the word or, A or B happening. Okay, so the probability that A or B happens is the probability that A happens plus the probability that B happens, but it's really important that that condition is that they are mutually exclusive, otherwise this doesn't work. All right, our last theorem talks about complements. Again, more notation from Math 1. This symbol right here, the A with the line on the top of it, means the opposite of A. We use the phrase not A, or most mathematically correct is the complement, and it's not complement like, hey, you look great today. It's spelled different actually, even complement of A. I always have fun correcting the spelling of that particular one when I grade stuff. So complement, it's all E's, no I's in that one. All right, so this is saying if A is an event and A bar, not A, is the complement of A, then the probability of A plus the probability of A complement equals 1, and then the other two formulas underneath it is just moving things around with algebra. All right, so this is something like this. You look at the weather, and you're going, oh my goodness, there is a 40% chance of rain tomorrow. And we always get a little anxious at that point, right? But come on, what's the probability that's not going to rain? 60%, right? How did we get 60%? They have to add up to 100, right? And that's all this is saying. This is saying the probability the event happens compared to the probability that it doesn't has to add up to 100% or a total of 1 if you're doing it in decimal form. That's all this theorem says at all. Okay? All right. So let's take a look then. There is a beautiful list where they put them all together for you, and you're going to write them all in for me. So I'm going to just pause for a second, let you transpire all of those, and then we'll talk through them and make sure they're okay. Okay, I think most of you are getting close, if not done. Let's take a look at these one by one. The first one has a name. It's called an impossible event. We gave an example of this one earlier. I didn't write the notation down, but this would be something like the probability of rolling 0 on that die, right? Can't happen. Okay, the probability that when it's 80 degrees outside, it's going to snow. Not going to happen, right? That's an impossible event. The second one is the probability of the whole sample space happening. That's what S is representing here, is sample space. So what's the probability that the whole sample space would happen or anything in the sample space would happen? Well, 1, because the sample space is all the possible things that could happen. Right? It's going to be one of them. So that's a certain event. It's definitely going to happen. The third one, we already wrote down that all the probabilities are going to be between the 0 and the 1 for any event. The fourth one is that if the events are mutually exclusive and you wanted to find the probability of the event A or event B happening, you can just add the individual probabilities together. So write the probability of even being rolled. You can add the probability of a 2, a probability of a 4, and a probability of 6. Okay? Let me skip this one because this one's going to require me a little bit more explanation since we haven't talked about that one yet. The last one says the probability of the complement of an event happening is 1 minus the probability the event happens, and that's that 100% minus the 40% chance of rain question we had before. All right, so let's take a look at the fifth one because that's the only one we haven't discussed. And we're going to talk about this with that die again. I told you you're going to keep coming back to that rolling a die. Let's say, for instance, that event A. Actually, take a look at between this one and this one. Tell me what is not known in number 5 that is known in number 4. What condition do we have in the fourth example that we don't have in the fifth one? Yeah, this part, right, Haley? The fact that they are not necessarily mutually exclusive. That's the piece that we don't know. So what we're going to create here in this example is we're going to create something that's not mutually exclusive and see how this all falls apart. All right, so let's just say that event A is that we roll an even. We did that one before, right? And let's say that event B is that we roll a 1, 2, or 3. These are not mutually exclusive events. What do they have in common? 2. 2 is in both of their sample or both of their lists of events, right? Yeah, it's an outcome in both of them. So let's take a look then what happens when we calculate these. What is the probability of rolling an even? And let's do it out of 6s, because I think it'll be easier to look at that. Probability of rolling even, 3 out of 6. What is the probability, part B, of rolling a 1, 2, or 3? 3 out of 6. What happens if I add these together? You get 1. Why does that not feel quite right? It's not all the options. In particular, what's missing? 5. So how in the world are we missing event 5? What is it that contributed us to getting a 1 when we shouldn't have? The 2 was counted twice, wasn't it? Because it was in both lists, it was counted twice. So what this says up here that we should do when we're counting these is, yeah, we're going to add the 3 over 6 and the 3 over 6 together. But this piece right here says that I need to count whatever's been double counted and remove it. So in particular for the problem that we're working with here, we had 3 out of 6 plus 3 out of 6. And the one thing that got double counted, the number 2, would have been a 1 out of 6 probability. And sure enough, if I do and take out that 1 out of 6, I get the 5 out of 6, which actually is the 5 options that happen when you consider event A and event B. So there's this extra sort of like taking out anything that is double counted if you're choosing something where the events do somehow overlap one another. Any questions on that one? Okay. We're going to move out of the realm of dice and we're going to look at cards. All right, so I know that not all of us are as familiar with cards as maybe your classmate is or something. So let's just talk a little bit about some things about cards. If you are not as familiar, you might want to jot some of these down. If this is old hat to you, then feel free to just listen, okay? So in a standard deck of cards, how many cards are there? 52. That's important to know. There are 52 cards, okay? What colors are the cards? Black and red. Those are our usual colors. How many of each color are there? 26. 26 black, 26 red. You're answering a different question. We'll get to that one in a second. All right, there's 26 black, 26 red. What are on the cards? I mean, what values, we'll say? What kind of things do you see on them? 2 through 10. So there's some number cards, right? 2 through 10. What else are there? Ace, king, queen, jack. And those are called face cards with the exception of ace. And ace is not considered a face card. It's also not a number card. It sort of doesn't get to be in either category. Okay. There are 4 what we call suits of cards. What are the suits? Clubs, diamonds, hearts, spades. All right, so which suits are red? Hearts and diamonds. Which suits are black? Spades and clubs. Okay. How many of each suit are there?
13.
That's the 13 we were looking at before. 13 clubs, 13 hearts, 13 spades, 13 diamonds. How many are there of each value card? There are 4. So there are 4 queens, for example, right? There's a queen of hearts, a queen of diamonds, a queen of spades, and a queen of clubs. All right, this question is asking us to consider taking one card out of a deck of cards at random and wanting to look at whether or not we are equally likely to get each of these 2 categories of things to have happen. So what we're going to do as we look at this is we're going to actually figure out what is the probability of each of these things happening. The question doesn't specifically tell us that we have to find that on this one, but we can make this justification better if we've actually thought through what that should be. So take a look. Face card. So how many, well, what were our face cards? Let's say that first. What were our face cards? Jack, queen, king. So how many jacks are there?
4.
How many queens? How many kings? So how many face cards are there? 12. Out of how many cards total? 52. Fantastic. How many cards are not face cards? 40. It's everything that's left over, right? Out of 52. Are these events equally likely? No. You are much more likely to draw something that is not a face card. Okay, clubs. How many clubs are there? We said this a second ago. 13 out of diamonds, hearts, and spades. Are these equally likely? Yes, they are. How many black cards are there? 26 out of 52. It's always out of 52, right? Okay, good. And red? 26 out of 52. Are these equally likely?
Yes.
Yes. Okay, how many kings are there? 4 out of 52. Queen? Jack? Ace? Okay, now if the problem stopped here, would these all be equally likely? Yes, but it doesn't stop. How about even cards? 20 is right. I count 20. Right? 2, 4, 6, 8, 10. There's 5 of them, and there's 4 of each of them. Each of those 5. So there's 5. There's 4 2s, and there's 4 4s, and there's 4 6s, and so forth. Right? Okay. So there's 20 out of 52. How about odd? There's only 16 out of 52 of those.
How did you get that with this?
There's 4 of each. So there's 4 2s, 4 4s, 4 6s, 4 8s, and 4 10s. So those are the 5 numbers, and there's 4 of each. That's 20. The problem with odds is that we don't have from 1 to 10. We only go from 3 to 10, actually, with the odd numbers. 3 to 9. Huh?
Right.
Yeah, so 3, 5, 7, 9. So there's only 4 odd numbers, and then times 4 each. Okay, are these equally likely? No, of course not. No. Okay, so there's this idea of calculating and checking whether or not things are equally likely to happen. Now we'll do an example that's not gambling. And we're going to talk about a Civ class, because you guys just love Civ, don't you? All right. These are all made-up numbers. I have no idea who's in your Civ class. But I am guessing that there's probably more girls than boys. Yes, I'm getting nodding of heads. Okay. All right, so a Civ class is composed of 21 men, 34 women. And then in my made-up Civ class, there are 22 education majors, 13 religion majors, 12 science majors, 5 English majors, 3 math majors. And if I put all the numbers in there right, that should add up to the total people in the class. We're going to hope so. I've used this example before, so let's hope. All right, it says, assuming that no one has a double major, and we need to know that, right? Why do we need to know that? Yeah, nothing got double counted, right? Okay, that's an important piece of information. If a single student is chosen at random, what is the probability that the student is ... We've got some examples. So let's start with female. What is the probability that the student is female? Okay, where did 55 come from? Fabulous. So 21 plus 34 is 55 apparently, yes? Good. All right, so there's 34 out of 55 chance that you actually selected a female when you selected at random. What about a science major? 12 out of the same 55, right? Yeah. How about an English major or a religion major? Okay, so where did the 18 come from? Okay, so we added the 5 English majors with the 13 religion majors. Sorry, it's off my screen. Yeah, good. So there's my 18. All right, there's 2 ways to do part D. Okay, so take a second. Don't say anything out loud. Answer the question. Neither a math major nor a science major. Think through how it is you're making that determination. Write down what you think it is. And then we're going to talk about the 2 different ways that we could calculate that. Okay, so you should have an answer of 40 over 55. We'll reduce it in a second, but do we have a 40 over 55? Okay, great. So somebody tell me, Lauren, I'm going to pick on you today. Lauren, tell me, how did you get 40?
Well,
What'd you do?
I did 12 plus 3, which is adding the math major and the science major, so you get 15. And then you subtract 15 from 55, and you get 40, which is the total number of students that are not math and science.
Excellent. Okay, so this is one way to do it. We can figure out how many math and how many science we have combined, which is what Lauren did. 3 and 12, so that's 15. And then we can take that away from 55. Who did that? Okay. If you didn't do that, what'd you do? Kayla?
Added all of the others, so religion, English, and education together because they're not in that percent.
Okay, so the other option is to add the things that are not in these categories actually together. So we can add the English, the religion, and the education together, and if we do that, we also get 40, right? Yeah. So those are two quite different ways of doing it, right? There will be times when it makes more sense to do the add these numbers together, take them away from the whole total. And there will be times when it makes sense to add the desired outcome together itself specifically. And it depends a lot on the situation we're in. So as we come across those, we're going to refer back to this idea in a future section of Chapter 9. All right, let's do one thing, though. You guys gave me an answer. It was 40 out of 55. We aren't going to leave that in an unsimplified form. What can they both divide by? 5. So if we divide by 5, what do we get? 8 over 11. Very good. All right. Here is a student who is claiming that if a fair coin is tossed and comes up heads 5 times in a row, then according to the law of large numbers, the probability of tails on the next toss is greater than the probability of heads. What is your reply? Did you just laugh at them, Melissa?
No.
No, that wasn't me. Okay, so there's some errors in reasoning here going on. So somebody tell me one error, just one. Restrict yourself to one error in reasoning that's going on.
Isn't large.
5 isn't large. Okay? That's definitely something that we probably want to mention is that 5 isn't large. Okay, so let's change our student, and he says, no, I didn't mean that it was tossed and came up heads 5 times in a row. It came up heads 50,000 times in a row. Okay, so he changed it. Now we don't have the large issue. We still have an issue.
Probability doesn't change. Like, the past doesn't matter how many times. There's probably as long as we have.
Yeah. So this is sort of issue number 2, is that every event, specifically of tossing a coin, because that's the event we're looking at here. Some events, aren't completely what we call independent. They do affect one another. Whether it rained yesterday does have some bearing over whether or not it rains today, right? We can't always say this. But when we're flipping the coin, this is definitely one event does not affect the other one. So the event of tossing a coin once or even multiple times does not affect future or past, but future events. We have a word for this. I haven't defined it yet, but I will right now just write it down. The events are independent. That means they have no effect. Independent of one another. This is the reason that you cannot say that just because someone has had 5 girls and they get pregnant again means that they're going to have a boy, right? Does anybody know anybody with like lots of children all the same gender? I do. I know a family with 6 girls. Nodding heads. Do one of you have that happen in your family? 4 girls. Yeah. Okay. So each event is independent of prior events, right? They don't have a bearing on one another. Although I do have a friend from high school. It's a guy, and his wife. They already had 3 girls, and she got pregnant with twins. And in his Facebook post announcing his gender of his children, he said, "I must officially have no Y chromosomes," because he had twin girls after that. 5 girls. Fun stuff. So, all right. So we have 2 separate issues going on with this particular student that we would probably want to address. All right. Let's take a look at a spinner. The following spinner is spun 1,000 times. I think 1,000. No, it says 100 on both. Okay, 100 times. Joe claims that the number 4 will occur most because it has the greatest area of space in the spinner. What would you tell Joe about his conjecture? What is the probability that 4 will occur on any spin? Okay. Okay, because this is a spinner. Oops. That's definitely wrong. The wrong class of material right there.
I didn't laugh at that one.
Okay, we'll work on this blank screen right now. Okay, so we've got our spinner. I won't redraw it. You've got a picture of it. But there's issue with his little spinner, right? So what is the issue about what he said? He's talking about area, right? So how does that play? I mean, he's right. The area of region 4 is bigger than the other ones. So why does that not matter?
They're all 90-degree.
Okay, so spinners move through an angle, right? It's the angle that the spinner's going through, not the space that it's actually taking up in that region. All right, so in spinning, it's the angle the spinner goes through that matters. In this spinner, every region is a 90-degree angle. That's what you guys were telling me, right? So each region has what probability? Equal chance of occurring. The probability of spinning a 4 is what? 1/4. And you can think of that because 90 is 1/4 of 360 degrees. You can think of it that way. You could think of it as there are 4 regions, and all 4 regions have that same angle, so 1 divided by 4 because there are 4 equal regions. You can think of it that way. Any question about my spinner that disappeared? Okay. What about this? What if the previous question posed was the image of a dartboard? Would that change your reply to Joe?
Yes.
Yes. Why? In a dartboard, area, not angle, right, is what matters. More area equals a greater chance of, we'll use the phrase landing in, you could say hitting, landing in a specific region. Now, there is something that we can't do that we did before. Over here, I could actually tell Joe how likely it was that he could hit the 4. I can't do that here, right? I would need more specific information about how this is actually divvied up. Agreed?
Yeah.
All right, so we're going to actually just make that comment and say something like this, but without more details or more specific information or something like that. We can't figure the probability of 4 in this dartboard.